Okay, thanks very much. I'm Mike Chaffin, and I'm here representing MAVEN, which may be a surprise to some of you because MAVEN's all about the atmosphere, right? But we did have a chance to take some observations of Phobos, and I'm going to tell you about them. Okay, so the reason why MAVEN had a chance to observe Phobos is because of the design of our orbit. The orbit's elliptical, and it's designed to process and cover the entirety of the Mars atmosphere, thermosphere, ionosphere system, but it's also designed to get us out into the upstream solar wind. So what you see here is a projection of the MAVEN orbit over the course of the first year. One of the orbits is just an ellipse here. The first year of the mission covered a wide range of the territory around Mars, and it turns out our apoapsis is right around the orbital distance of Phobos, so we periodically have close encounters with the moon. That poses a navigational challenge, but it also gives us an opportunity to do science when we have a close approach. MAVEN does its science with a whole bunch of instruments which are optimized to study the ionosphere and thermosphere. Most of these are charged particle instruments. We have a neutral gas and ion mass spectrometer, and we also have an imaging ultraviolet spectrograph carried here on this articulated payload platform which hangs off of the bottom of the spacecraft. I'm going to be focusing on the data from this instrument, which is detailed in this slide. So MAVEN's up here, we hang off the bottom, and between the spacecraft and the instrument are two gimbals which allow pointing capability for the instrument. That allows us to observe independently of the orientation of the spacecraft. Most of those instruments want to be pointed at the sun all the time to get solar parameters. But with these gimbals, we have a great deal of freedom to orient the instrument as we choose. We have an additional internal degree of freedom which comes from the scan mirror, which allows us to point anywhere in a limb or a nadir port, allowing light into the instrument from any of those directions. Light passes into a pretty standard grating spectrograph with a few bells and whistles. So for example, we can flip this grating out and have in a shell channel to study hydrogen escape. But with the grating in the normal position, we observe simultaneously in the MUV and the FUV, with FUV light split by a beam splitter and going to its own separate detector to suppress stray light. These are the wavelength ranges that we're covering in the far ultraviolet from around 110 to 190 nanometers, and in the mid ultraviolet from 180 to around 340 nanometers. Here's a picture. So the long dimension of the instrument here is about 60 centimeters. So as I said, periodically we encounter Phobos. This gives you an idea of what the orbital geometry looked like last November in 2015 when we performed targeted observations. This is the first time we attempted to perform targeted observations of Phobos. So MAVEN here was in sort of a terminator along the terminator orbit, and at its closest approach to Phobos when we gathered this data, the two objects looked like this. As I said, we did two targeted observations. Each of these was partially successful. In the first sequence, which took place on November 11, we obtained MUV spectral images, but those images were corrupted due to a commanding error of the instrument, which didn't allow quite enough readout time. We were still able to sort of put the photons back where we thought they should have come from and generate some pictures, but these are corrupted, so we can't really do any science with them. But in the second targeted observation, we obtained one complete MUV and FUV spectral image, which you see here, and I'll talk about this a bit more. These colors are wrong. I'll correct that later. Okay, so I'm going to focus on the analysis of the MUV data, which you see here in orange. Blue shows you Lyman alpha light that's scattered off of the extended atmosphere of Mars and blocked by the moon. As you can see from the geometry diagrams here, Phobos is on the side of its orbit where it's moving back toward the night side of Mars. So this is the trailing hemisphere of Phobos. As far as I know, this hemisphere has never been observed in the UV. Peng et al. 1978 report a Mariner 9 UVS spectrum of the leading side of Phobos. So this is the first UV data that we've gathered on the trailing side of Phobos. Gathering this data was a little bit tough because, as you can see here, the orbits are inclined with respect to one another, so the relative velocity is high. At closest approach, we were about 300 kilometers away, and the relative velocity was about 3 kilometers per second, which means that Phobos was moving about a degree per second on the sky. That's not necessarily a problem if you have a camera, but we have a slit spectrograph. And so to make an image of Phobos, we need to perform some detailed commanding of the instrument and take advantage of the ability of the spacecraft to orient our instrument independently of everything else that's going on. So a lot of work was done by engineers at Lockheed Martin to put the relative motion of Phobos on the sky along the field of view of the instrument. So Phobos passes directly down the middle of our field of view, and then we can use our internal degree of freedom with the position of the slit to map Phobos. So what you'll see here in a moment is this pink dot, where it's supposed to represent the approximate size and position of Phobos. It's going to start moving, and we're going to paint backwards over it with the position of the slit here in this, which is our limb port. Down here you'll see a spectrum in the mid-ultraviolet, and this will fill up with an image of the detector with wavelength on the horizontal and the slit dimension in the vertical. This actually represents where Mars was with respect to the spacecraft at this time. Okay, so we tracked the moon pretty well. You can see it cross through our slit, and then thanks to some luck and a cooperative atmosphere, Phobos was exactly where we expected it to be, and this was a complete success. If you register this into the Phobos frame, this is what you get. So I've got the shape model in the background, which is constructed from camera data, the position of the slit as a function of time, and then you can see here all of this blue, which is 121.6 nanometer light scattering off of hydrogen in the extended atmosphere. That light is blocked by the solid body of the moon. And then on the day side of Phobos, we see this bright reflected MUV light. So we can actually observe the full moon, even though only half of it is lit, because we have this ability to image in the far ultraviolet. I'll call attention to the fact that we have a few specks of blue here on the day side. I'd say the density of those blue specks is higher on the day side than on the night side of Phobos. That tells you that Phobos is reflecting enough Lyman alpha light that we can probably get an albedo out of this data at Lyman alpha. We can map the data onto the surface of Phobos. So here you see the longitude and latitude in a projected view of Phobos. We're looking at the south pole of Phobos here. And if you put that down onto a map in longitude and latitude, this is what you get. So we're sort of antipodal to Stickney Crater, which is over here. I'll try to put both of these up at the same time, and you can see that the sunlit portion of Phobos here is again on the trailing side, on the opposite side from that big crater. So onto the spectra. You can see here our wavelength coverage extends from slightly below 200 nanometers to around 340. This blue curve here represents the uncalibrated spectrum and the uncertainties associated with that spectrum for 1 pixel in this image of Phobos. That represents 0.2 seconds worth of integration time. And I compare that with the solstice solar spectrum times the IUVS sensitivity. So this shows you what the sun would look like if it passed through with no noise through our instrument calibration. You can see the match is pretty good, but we can do even better if we add up all of the data on the day side. So this blue curve here represents a total of all of the sunlit pixels here on Phobos. And that represents a total of about 40 seconds worth of integration time, which is all we could get with the orbital geometry that we had moving past Phobos at this high velocity. And if you divide these two out, this is what you get. So in gray here, you see all of the sunlit pixels individually. That gives you an idea of the spread in the data set. The black represents the mean of each of those, of all of those gray spectra in each spectral bin. And then you can smooth that out to account for some inaccuracies in the spectral alignment of the solar and detector spectrum with a 5 nanometer Gaussian smoothing, and you see this red curve here. So the peak brightness here relative to the sun is at around 275 nanometers. This confirms what Amanda was talking about earlier with regard to the Mariner spectra. You can't really believe this increase on both sides of the detector because we're losing sensitivity at the edges. We don't really have a good understanding of our calibration out there because we haven't spent enough time staring at stars to really pin it down at those edges. But this dip longward of about 300 nanometers is probably real. So we're seeing the same thing in the newly calibrated SPECAM data, the Mariner 9 data, and in IUVS here. If you put up the Mariner 9 data from the Peng et al. Paper, this is what you get. You can see it increases here, but maybe that's an artifact of the calibration. So Amanda's nodding, so I'll take that as a yes. It does have this dip here at 300 nanometers, so maybe they had the same issue with the calibration giving out on the long end of the detector. But this spectrum from the leading side is more steeply sloped toward the blue than our IEVS spectrum of the trailing side, which perhaps indicates compositional differences or maybe even differences in space weathering. On the moon, for example, more weathered terrains are bluer in the near ultraviolet portion of the spectrum. That's something that Amanda really hammers home in a couple of her papers. So we're seeing a difference here between the trailing and the leading side of the moon. We don't have FUV data at the moment, and that's because, as Amanda mentioned, the spectrum of the sun is really falling off in this wavelength range. So we had, this is about the minimum usable signal that we had in our current observations. We get useful data at Lyman alpha and in the near and mid ultraviolet. But to get down into the FUV, you really need about 50 times as long to observe. We can do that, and we plan to do that in future campaigns, but we're not there yet. So to summarize, IEVS observed Phobos in dedicated imaging campaign in November of 2015. We've learned some things from that campaign, and we'll be continuing to learn some more things. That gets the take home I have right now is that based on the Mariner 9 data, the trailing side of Phobos is bluer than the leading side, and we'll be able to get a Lyman alpha albedo of the moon out of this that'll add to just a handful of measurements of Lyman alpha albedo of solar system objects. So I said in future campaigns we'll be able to observe different locations on Phobos. We'll be able to build up our signal to noise and maybe get an FUV spectrum. Just to give you an idea of when these future observations might occur, we have encounters actually starting this month and going through September, but we're not going to target those. And that's because our apoapsis is on the day side at the present time, and we've never had apoapsis on the day side, so there's a lot of the Mars surface to look at, and we can also take advantage of the side segments to do really great coronal scans and fulfill our primary mission of measuring atmospheric escape. But there are a number of other seasons when we will be encountering Phobos near the terminator, and then here near the anti-solar point, and we'll build up dedicated sequences to take advantage of those opportunities in the future. And with that, I'll leave my conclusions up, and I'm happy to take your questions.
I'm not sure if this is a better question for you or Amanda or both. And it's probably obvious. You talked about, or I guess Amanda talked about, comparisons of the UV for Phobos to other asteroids, to asteroids or to the moon. How does it compare to Mars itself?
Yeah, so that's a tough question to answer because Mars has an atmosphere, which does a lot of scattering. But maybe you can address that question better than I.
Yeah, well, I think you're exactly right that the atmosphere is absorbing in the UV, and so usually that ozone signature dominates when you look at Mars. So it looks completely different.
We do gather data on the surface of Mars in every single orbit with MAVEN. And the reason why is to look for that ozone absorption feature. But there is information in there potentially about the surface as well.
Yeah, is it possible in theory to remove the ozone signature, or is it so bright, so absorbing that it saturates and you don't get anything?
So I'm not an expert in this area, so I can't answer your question. My impression is it would be hard.
I have a question.
Yeah.
Do we have time? I don't know what we have. Okay. Let's see. The spectrum that you showed us from the day side, was that the day side averaged?
Yes.
Or can you get any spatial information?
Yeah, so I looked for spatial variation, and it's really pretty bland as far as I can tell. So you saw in that spectrum, the ratio with the sun at the end, I showed gray curves for every single pixel. And I didn't see any bifurcation or any distinct sorting of those gray curves. So it looks like from where we were observing and the locations that we were observing at the time that it was pretty spectrally uniform. That's not to say that if we looked at the other side, we wouldn't see a completely different spectrum.
One more question. This is a question not related to the UV on spectrometer on MAVEN, but this is related to other instruments like the mass spectrometer. Do you know if during the next campaign it is scheduled some measurements close to Phobos with this instrument?
Yeah, so we did use all of the instruments when we did our close flybys. So all of the charged particle instruments were put into their periapsis mode, which we use to get the highest sensitivity data, and they did not see anything which could be unambiguously attributed to the moon. Now, as I understand it, you kind of have to get lucky in order to be connected magnetically to the moon when you fly by. So it's possible that these effects exist and the configuration of the magnetic fields just wasn't right for us to observe any ions being sputtered off the surface. We will have encounters with Phobos. They're going on now and through August, and the instruments will be on all the time during those encounters. So it's possible we could get lucky in the future.
And what will be the closer encounter distance?
Yeah, so we try to not get any closer than we got at this time. So we execute maneuvers to stay a couple hundred kilometers away at the closest. It's possible for us to execute maneuvers to get very close to the moon, but we haven't done that. And in fact, we just got lucky with this 300-kilometer approach. That's just how the orbits aligned. So we took it. We don't plan to execute any maneuvers to get close to the moon. We'll just take what we can get. Thanks.
Thank you.